problem. Okay, thank you everyone for being here. I will just briefly introduce myself. My name is Samir Kouro. I am a professor at Universidad Técnica Federico Santa María in Valparaíso in Chile. And I work, well, actually in this, I brought some pictures here. So I work in this university, it's in Valparaíso. It's in the central region area of Chile. And I work in two research centers. One is AC3E, which is the Advanced Center for Electrical and Electronic Engineering, and also at SERC Chile, which is Solar Energy Research Center, which is a consortium of several universities. Here are some pictures of AC3E. Well, so I will talk today a little bit about photovoltaic energy to produce with that green hydrogen. So, and it's just a brief introduction from a power electronics perspective. So I'm not a chemical engineer. I am an electronics engineer. So that will be the main scope, if you will, of the presentation. Quick disclaimer, I'm not an expert in the chemical part of it. So in case that I don't have the specifics on the electrolyzers and stuff like that. I brought a little bit of information about that, but of course it's more from an electronics engineering perspective. Also, another thing is that parts of this presentation are included in this paper entitled Photovoltaic Green Hydrogen Challenges and Opportunities. We have co-authored this with a group of colleagues, Hugues, Renaud Dinot, Ana Yor, Raúl Cortés, Cristian Rojas, Carlos Restrepo, and myself. This is a paper that got recently accepted and is currently in early access in the IEEE Industrial Electronics magazine. Here's the digital object identifier. So many of the things I will talk about today are included in this paper as well. So the reason why we are talking about green hydrogen has to do because of the environmental crisis, climate change we are now living in. And of course, we know this is generating a lot of changes in our climate and in our way of living, and it will impact even more if we don't do something about it. So this is, of course, something caused, as you know, mainly by the energy sector. So in order to mitigate the effects of this phenomena, it's also something that we have to solve from the energy sector as well. And the big problem is greenhouse gas emissions, as you know, and 70% of it comes from fossil fuels, mainly. Around 25% comes from agriculture and other uses of soil. So that would be the main area not related to energy. All the others are somehow directly or indirectly related to fossil fuels. And from this, transport alone is 14%. So this is forcing in an energy transition. We have to move away from fossil fuels, and not only because of climate change, but also fossil fuels are limited in reserves. It's not a renewable source, so that's why it's also ever increasing in costs, of course, because it's getting scarcer and scarcer. Even if they find from time to time new oil and gas sources, it will eventually increase over time because it's just a limited resource. That's how it is with limited resources, right? And the other thing is that if you look at this map, those continents where you have lower resources of fossil fuels are the ones that are in the highest amount of poverty or underdevelopment. Of course, that's a multivariable issue. It's not just related to fossil fuels. It's also cultural and historical things and whatnot. But there seems to be an interesting correlation there anyway. And so if we look at the energy transition map of technologies, according to this website of the World Economic Forum, there are some areas in which we are kind of doing okay, which is the light blue circle. And that would be in solar photovoltaic, in electric vehicles, in lighting technology, that's basically LEDs, also data centers, although I don't agree with that all, but per se, I think we are better in these other areas than in this particular area. But according to them, we are quite on track on those areas in terms of reducing the carbon footprint. If we go into the middle circle, these are areas in which more effort is needed, and the darker circle is the one in which we are completely not on track, in which we are lagging behind. If you want to meet zero net carbon at around 2050, right? So if you see the areas in which we are really lagging behind is transportation of larger scale, trucks and buses, international shipping, aviation. Those are areas in which we are really lagging behind. Also heat and cooling, carbon capture usage and storage is also an area in which we are lagging behind. Industry in general, chemicals, iron and steel, cement, pulp and paper. In all these areas, we are lagging behind according to our goals for 2050. So this is the reason why hydrogen is getting more and more attention recently, because there is so much of these applications that you can electrify. For example, it's very difficult to electrify an airplane, right? So we need to find an alternative in order to reduce the carbon footprint of aviation, for example, and ships as well, and so on. And it seems that hydrogen is kind of a possible solution. And the reason for this is that hydrogen is a very good energy carrier. It's very high in energy density. So it's good for storage and use it in mobile applications for, let's say, buses, trucks, planes, and so forth. I'm not talking necessarily as its natural form, as hydrogen, maybe as a synthetic gas or liquid fuel. So you can convert hydrogen into methanol, and from methanol you can go to kerosene, and you can go to diesel as well. And those are synthetic fuels. Of course, they are more expensive than natural fossil fuels, but these ones, if they come from green hydrogen, then they would have, of course, a very low or even zero carbon footprint, and that could be unlocking somehow the possibilities for aviation and ships and large trucks and so forth. So that's another reason why. Also, it can be transported fairly easily and distributed via conventional methods. So we have already pipes to transport liquids and gases, and we also have containers and trucks that we use in the petrochemical industry. So it's not something that would not be available in terms of technology to transport hydrogen, right? And it can also generate heat and electricity. So it's very versatile in that respect. And this is why it can be used for several of these energy transition applications. And so depending on the production method, depending on how you produce this hydrogen, then we could be talking about something that is carbon neutral. And that's where green hydrogen comes into place. I will explain a little bit what green hydrogen is in a minute. But this is just to show you where we stand in 2020 and what the projections are for 2030 and 2050. So currently, hydrogen doesn't even appear in terms of the net zero emissions, in the total final energy consumption. So if we see currently how much of the energy that we use on Earth is actually used as hydrogen, it's almost non-appearing on this plot. By 2030, it's going to be a small sliver here, and then by 2050, it's going to be around 10 to 15%. So hydrogen is not really a big thing currently in the energy sector, and the reason for that being is because it's an energy carrier. It's not an energy source, so we have to produce it first. And then the other thing is that the production of hydrogen currently is only 80 megatons per year. and it is expected to double in 10 years and then increase quite substantially for 2050. The other thing that's quite important to see is that hydrogen will not be the only fix to this problem of climate change and energy transition. Is going to be only a 6%, according to these estimates, 6% of the cumulative emission reduction by 2050. So we still have to advance in renewables, we still have to advance in electrification, in carbon capture, usage and storage, etc. So it's going to be an important part, but it's not going to be the only thing. It's not, hydrogen is not going to solve the problem by its own, right? But still it's important. So coming back to what's green hydrogen, so depending on the fuel that you use, the original energy source that you use to actually produce hydrogen, and depending on if it generates greenhouse gas emissions or not, it receives these colors, these schemes of colors. So if it comes from coal, this is the one with the highest greenhouse gas emissions, and we call it brown hydrogen. It's fairly cheap nowadays, but it's not produced massively as brown. So the 20 megatons we talked here are, although it's mainly done by fossil fuels and a bit as byproducts, it's not mainly done by coal. It's actually gray hydrogen, which is done from natural gas reforming. So we reform steam methane, and that produces hydrogen. And we call it gray because it still has quite a big greenhouse gas emission impact. If we use carbon capture and storage, then you reduce very substantially the emissions of greenhouse gas emissions, and then we call it blue hydrogen. And of course, that's a little bit more expensive because you have to have a system for carbon capture. But this is actually quite a good intermediate solution. And then we have green hydrogen that comes from renewable energy. So mainly photovoltaic and wind. And it's done, instead of gas reforming, this is done by electrolysis. So here we split the water molecule into hydrogen and oxygen, and that's how we produce both gases. And this is more expensive, primarily because the technology is a little bit more expensive, the electrolyzers, which are the machines that you use for doing the electrolysis, and also because of the energy source. So it's still around double of what we have in blue and gray hydrogen. And this is why, if we see our previous plot and we see the current scenario in 2020, the 80 megatons that are being produced are mainly done with gas, and also gas with carbon capture, and a little bit by byproducts of other processes. So we are quite lagging behind in the area of green hydrogen, but there is hope. I mean, in the sense that there is a big opportunity here, because renewable energy is continuously reducing its levelized cost of energy. So this cost will reduce over time. And also the technology used for electrolysis is quite recent, if you will, in terms of not the technology itself, but the maturation process and the commercial readiness level. So there are not many companies producing these machines, and that's what happens also when we had, for example, 10, 20 years ago, when only a few were producing wind turbines, and the technology was rather new. Wind turbines were very expensive, the same with solar inverters and solar PV modules, and they drop over time. So this is expected to also happen with the electrolyzers. So what's hydrogen then being used today? We talked about this 80 tons. Here you can see it's a little bit more than 80 actually. Here you can see that the production and the demand. So it's mainly used for chemicals and refining, and a bit for iron and steel. Here's a little bit more about the chemical industry. So most of it is used to produce ammonia and methanol. Okay, so those are the uses for which we mainly use hydrogen today. So probably if you are more new to the subject, you have only heard about green hydrogen and how it can be used for fuel cells in electric vehicles and buses and stuff like that. But actually, it doesn't make even a percentage on this plot here. It's marginal so far, right? So unfortunately, this plot is not looking great right now, but what I was showing here was how this around 90 megatons are spread among refining, ammonia, transportation. Here you can see how small transportation is right now, and also methanol production, which and here are the origin. And here in the origin, you can see that we have only 0.1 megatons produced from renewable energy, and 0.3 that comes from byproducts also related to renewable energy. So all in all, there is less than 0.4 megatons that comes from renewables, hence green hydrogen. And the other important thing to notice is that gray hydrogen is then, of course, not even a solution. It's actually a bad thing. So gray hydrogen is actually generating 900 megatons of CO2 emissions. So it's actually contributing to climate change, right? So why do we want to change this? Why do we want to move to more green hydrogen production? Because we want to unlock these potential applications over here in transportation for fuel cell in EVs, in buses, trucks, and ships, maybe some buses, trucks, and ships, and even some vehicles, but not electric vehicles, will do combustion of synthetic fuels. So these are fuels made from hydrogen. So you start from hydrogen, for example, you mix hydrogen with CO2 and you end up with methanol, and then you can use methanol to produce kerosene and diesel. Of course, it's way more expensive than from fossil fuels, but at least this one is green. So this can be used to feed conventional trucks, ships, and even planes. So that could be the way we actually fly in the future by airplane. Also residential and buildings to generate heat, also electricity, and industrial applications also, of course, to generate heat and electricity. Mainly also it will remain for refining and also for power generation. So here you can see a little bit the breakdown of the projections on how the green hydrogen actually would be used. This is not just for green hydrogen. So the 80 or 90 megatons will increase over 500 in 30 years. And here you can see a little bit the breakdown in terms of energy, in terms of application area. So you can see transport will become quite important, and synthetic fuels also, which will also be mainly used for transportation. And then you have other ones, buildings and refining. Here you can see how refining, which is the main portion of today, is going to be a smaller portion in the future. This is a way, just a diagram to explain what I just said, but here you can see a little bit the flow path of hydrogen on how it can get into synthetic renewable fuels, which is through methanol. So you start from water and renewable energy. This could be wind or solar, and then you produce hydrogen. Hydrogen plus CO2 generates methanol, and with methanol you can go to synthetic fuels. You can also, of course, use hydrogen also in fuel cells and also to generate heat and electricity and so forth. Of course, oxygen is also a byproduct of this production, and you can also use oxygen for other applications as well. So how is going to evolve the cost of green hydrogen compared to gray and other ways of hydrogen? And that's being shown here. So here you have gray hydrogen without carbon capture. This is with carbon capture. And this is coal without carbon capture, coal with carbon capture. And this is based on renewables. And here you can see this is a current picture. So This is the lowest end and the highest end of the cost of the levelized cost of hydrogen. The levelized cost of hydrogen is basically a methodology that we use based on the capital expenses and operational expenses for hydrogen production. And it's based usually on 15 years. And this enables us to compare fairly the different sources of hydrogen. Of course, the levelized cost of energy is done on the same methodology. It's also mixing capex and opex, but it's done for photovoltaic, wind, and so forth. So levelized cost of hydrogen is actually the same concept of levelized cost of energy, but applied to hydrogen. It does not include storage, transportation, and distribution costs. That's something that most of the websites and agencies that are calculating this are not including. So that's also worth noticing. And it's usually measured in US dollars per kilogram of hydrogen. So here you can see that, like we already showed in some slides previously, I'll just go back to those slides. Sorry. Here you can see how gray hydrogen is between 1 and 2, while green hydrogen is between 3 and 7.5. Of course, this is from another organization. This one is from IEA, sorry. And here you can see between 1 and a little bit below 2. And here you can see that green hydrogen is a little bit higher, between 3 and 8. So depending on where you source your information, they will vary a little bit, about $1 or $2, but in all of them, green hydrogen appears substantially higher than gray hydrogen. And of course, it's expected to get lower by 10 years and 20 years. And most of the projections I've seen end up having after 20 years. So by 2050, in some areas of the world, getting more cost effective than gray hydrogen. So here you can see actually where this happens. This is the mix between hybrids. This is a mix between PV and wind based hydrogen. So not just photovoltaic, but also with wind. And here you can see where the levelized cost of hydrogen will be below $1.5 US. So this would be breaking even with gray hydrogen. And you can see parts of Chile, Bolivia and Peru, Argentina as well, also in the south, in Patagonia, areas in Mexico and the US. Canada has a lot of wind here up north, and the Sunbelt area, of course, and you have also areas here with good winds as well. So those areas, and Australia, I forgot Australia. So those are areas in which we will have very competitive levelized cost of hydrogen, of green hydrogen. And here you can see some breakdown of some countries, leading countries expected to have the lowest levelized cost of hydrogen by 2020 and by 2050. So you can see 2020 is the one with the square, and the one with the sphere, the circle, is 2050. So of course, the lower ends will be by 2050 and the higher ends will be for 2020. And here you can see that China and Chile and also Australia will be the ones with the lowest, also the Middle East with the lowest in terms of photovoltaic. And then you have United States and China, if I remember correctly, yes, with offshore wind will be, and Europe will be, this is mainly UK, Belgium, Denmark, and so forth, will have very good offshore wind. So those will be the lowest levelized costs of hydrogen by 2050. And I believe this is the last, or I think this is one is maybe the last, or I have one more regarding levelized cost of energy. This is again how onshore, offshore wind will compare with solar PV by 2020, 2030, and 2050. So if we follow the circles, which is the one by which will be by mid of this century, is of course at the lower end. So all the circles you find here at the lower end, and all of the squares, which is the current scenario, are at the top, because there is where you have the highest levelized cost of hydrogen. And then If you go to the levelized cost of energy, which is in US dollars per megawatt hour, you can see that photovoltaic, whether it's in 2030 and 2050, will be at the lower end, and then followed by onshore wind and offshore wind, which are the ones that you see over here, right? So here we're talking about around 10, 11 US dollar per megawatt hour. And this is already the case in some places for solar PV. It's here, it says 20, but we know that in Mexico, some Arab countries, also in Chile and other areas, we have had below 20, biddings of 13 US dollar megawatt hour. So I believe that this is a little bit, it's a mild projection. I think photovoltaic will be lower than that in those areas. And so why will we focus in today's presentation on PV energy? The reason is, and PV to hydrogen, I mean, and the reason is because, like I just mentioned, PV is the one that has, if you do any sensitivity analysis, are the ones that really go into the lower end of $10 per megawatt hour. And in that area is where you reach the capex for electrolyzers that are really, really low, right? So this is really promising, and this is what makes us believe that PV-based green hydrogen will be something important from 2030 onwards. Okay, so going now past the economics and the numbers, now entering technology. If we go into the electrolyzers, we have currently, if you look in the internet, you will see some really big classification of electrolyzers. So electrolyzers basically, what they do is they split the water molecule into hydrogen and oxygen. And there are many ways of doing this. Even there are some ways without electrolyzer. You can do it also with photocatalytics and also with thermal energy, but those haven't reached anywhere near yet to commercial products. So I will focus on the water electrolyzers, and then between those there are also multiple choices and differences, but I'm going to bring to your attention the three main ones. One, which are the alkaline electrolyzer, the polymer electrolyzer membrane, the polymer electrolyte membrane electrolyzer, and the solid oxide electrolyzer. This is also called AEM, PEM, and SOE. And here the only difference is where the water enters through. So I mean, in the alkaline electrolyzer it gets through the cathode. In the other ones, in the case of the PEM electrolyzer, it gets through the anode. Then in the solid oxide electrolyzers, it also gets through the cathode. And then they have a first reaction from the side where the water enters. So in this case, we will have the first chemical reaction in the cathode. It will combine with electrons, and this will break the molecule into hydrogen and also hydroxide ions, which will flow through the membrane to the anode. And they use the electrolyte here normally being used is potassium hydroxide, and also there are some alternatives that use a membrane, alkaline exchange membrane, which is a case which I'm showing here in the figure. And then when these ions get to the anode, they have another chemical reaction where they combine with electrons, and you then liberate oxygen. I will show the chemical reactions in the next slides. In the case of the PEM electrolyzer, water enters through the anode, and then here in the first reactions, you break the molecule and you liberate oxygen, and then you have 4 protons that go through the proton membrane and get to the cathode, and the protons are basically hydrogen ions, and then again they combine with electrons, and then you generate hydrogen. And then in the other side, you have again a different carrier. In this case, it's oxygen ions, and in this case, we have a ceramic materials electrolyte. And the other thing is that in this case, we operate at very high temperature. So this one is actually heated with steam between the different plates here to actually being able to produce hydrogen. And this one is a little bit less developed than these two. Actually, most of the current existing electrolyzers found in industry are based on the alkaline one. The most promising and newer ones are based on the PEM, and these ones are still under development and maybe very few models actually being commercialized. So here are the chemical reactions. You can see the cathode reaction, the carrier that goes through the membrane, and the anode reaction for each of these three different electrolyzers. And then you have the total reaction at the end, which is basically hydrogen breaks down in, water breaks down into hydrogen and oxygen, right? Usually, to balance this correctly, you have here 2 molecules of hydrogen, which generates 2 molecules of hydrogen and 1 of oxygen. Here is how a typical alkaline electrolyzer looks like for real. So here you can see one cell. It's made of a cell frame, the electrode. So these are the 2 electrodes, the cathode and the anode, and then you have the membrane in the middle, and then you have a gasket and also the cell frame. You have the holes for the hydrogen and the oxygen recollection. And then you press pack this completely into one sandwich, and then you use many of those and you press them all together. And here you can see those 2 tubes will be going through these 2 holes over here. So that's how a typical alkaline electrolyzer looks like. They're very big. Doesn't show here in the picture because there's nothing to compare it to, but this one is almost 2 meters high and 4 to 5 meters in length. And this is how a typical PEM electrolyzer looks like. So the construction is a little bit different. Here you have a plate which has some holes which make like a spiral where water flows through and interacts with the diffusion layer and the electrodes. And then it's where the oxygen is generated and water. So here you get oxygen and water through. Then you have to actually dry. The same on the other side for the hydrogen. You have to go through a dryer to take the water out. Then you have this sandwich is one part of this, and then you have, of course, many of these cells stacked one after the other to generate the a higher voltage. Otherwise, you have here really small voltage. So you connect this in series to get a higher voltage levels. And here are 2 commercial examples, one of each. So this one is the alkaline, this is the PEM. Here you can see this one reaching, it's very modular in construction. The more cells you put here, of course, more power it accepts and more flow rate of hydrogen it generates. This one gets even up to 17 kVA. And these PEMs are a little bit smaller yet still, although they are increasing year by year. And this one is from up to 1.8 kVA. This is same company producing both technologies. So you can have a kind of a comparison of one compared to the other. So, but those are the electrolyzers. And of course, here, the electric energy you can use this doesn't have only the cells. This, of course, has a rectifier. This, I forgot to mention that you need the DC current here. You need these electrons in for the cathode and anode reactions. So those come from the DC source. And of course, so here you would have also a power converter to go from the AC grid to a DC current, right? So I will show some topologies later. But the thing is that if this electricity doesn't come from renewable energy sources like wind and PV, and it also comes from fossil fuels, of course, this wouldn't be green hydrogen, right? It would be electric based on electricity, but not green hydrogen. So now I will talk specifically, because that's the focus of this presentation, about PV to H2, so from photovoltaic to hydrogen technology. And much of this can also apply for wind energy, but I have made the presentation really focused on photovoltaic energy because of the larger, although they will coexist and they will mix together, as I showed in previous slides, photovoltaic energy is really increasing at a higher rate than what wind energy is doing right now. Actually, if you go back to 2010, in 2010 we had 400 gigawatt of wind capacity compared to the 40 gigawatt of photovoltaic capacity. And now in 2020, we are at 760 gigawatt of photovoltaic, and actually that's 2% more than what we have currently in wind power. So this is because of the levelized cost of photovoltaic is really going down in some areas of the world, reaching crazy values like $13 US a megawatt hour, while wind is still higher in those areas. So that's the reason why we're focusing on photovoltaic. And if we look at if we would like to integrate so photovoltaic power into this conventional, let's say conventional electrolyzers that connect to AC grids, then of course we have to have a conventional PV system that goes from the DC power to AC grid, right? So usually a PV system is composed of a DC-DC converter and a DC-AC converter. This one is optional. You can, depending on the configuration and the number of modules you have, and you can go without it. And of course, you will not have decoupled your DC link voltage from your PV voltage. And this is where a second stage, this DC stage, helps to decouple and optimize a little bit the inverter and the DC-DC stage. So as I will show later, most of the new PV inverters being commercialized are currently done in 2 stages. And why do we need actually this converter or the DC control of the inverter side is to actually being able to track this point over here, which is the maximum power point. So we use maximum power point algorithms for this. I won't enter into detail. It's not the focus of this presentation, but basically those are algorithms that gives you the voltage reference by which you generate the maximum power. And this is because these powers vary depending on the temperature and irradiance. So you have to actually be searching for them. And depending on the power converter architecture, you can connect one single PV module to the grid, which is called AC module or also microinverter. You can serialize the PV modules by connecting them in series, and then you reach higher voltages. And then you would have a string inverter. You connect a single string to the grid. This one has better energy yield because you have a single MPPT for a single PV module, while here you have a single MPPT for a whole string. So if you have partial shading on these ones, you won't be able to track these maximum power points that well, right? The thing is with the AC module or the string inverter is actually it's although it's shown here just as a single stage, but it's basically a 2-stage because you have a very low voltage over here and you have grid voltage over here, so you have to boost. And inverters don't actually boost, so you have to first have a boost stage of some sort. You can have isolation, so you can use a transformer to boost in the DC-DC stage, and then you have a buck inverter to reduce to the grid, right? So these are usually used for small systems, the same as with the string inverter. And then you have other 2 options, which is a centralized inverter, where you have a large string of modules connected in series, and then you have a lot of strings connected in parallel to reach the desired power. So you serialize to reach the voltage, and then you parallelize to reach the power. And then you use a single inverter to upload all that power to the grid. And that's usually a very large inverter, usually nowadays above 1 megawatt. There are even up to 3 megawatts. They are more economic and simple because you have a single control method and so forth, but you have a single MPPT for all the arrays and all the strings. So it's the one with the less energy production. And then you have a compromise between the string inverter and the centralized inverter, which is introducing a DC-DC stage here. With that, you decouple the DC link voltage from the central inverter from the PV voltage for the MPPT. So you get the benefit of a string inverter, and without having so much power electronics, because in the case of the string inverter, you need a full inverter for each one. Here, it's just a DC-DC stage, and then you have a single inverter for all those strings. So this is a good MPPT. This is a good compromise between MPPT and energy production, and flexibility and simplicity and so forth. But of course, it's a little bit more expensive than the centralized topology. Here are some pictures of those. This is just a summary about the AC model, the string, multi-string, and central topology, power ranges, devices, so forth, features, pros and cons, some configurations depending if you have isolation in the high frequency side, or isolation in the low frequency side, or if you are operating transformerless. And here are some commercial examples. You can see this table actually for further reading in this paper over here. And in this paper, you will also find most of the topologies that are currently found commercially found for the string inverters, the multi-string inverter, sorry, the string, the multi-string, the central, and the microinverters. And I want to stop here a minute, and that was just a brief introduction to just PV systems. But one of the things that has changed over time is that in the beginning, all the large-scale PV plants were done with things like this, a central inverter. But in the last 5 years, there has been a very big shift towards string inverters and multi-string inverters, basically multi-string inverters. So one of the reasons for this is that large central inverters, I already mentioned before that they have a lower energy yield because of the partial shading, but also they have more operational expenses and also more capital expenses because it's more costly to install. You need cranes, you have to operate this with a lot of people. And for 1 megawatt that you install, you can really install that megawatt really fairly rapid with the current large-scale large-scale or utility-scale tailored multi-string inverters, which I will show you in a minute. So the other thing is that those can be installed by 1 or 2 technicians, and also if one of these inverters fails, you have one up to 3 megawatt of your PV plant also off grid. And while if a smaller inverter fails, just 100 kilowatts, you have only 10% of that off grid, and you can just do maintenance on that or repair that, or you can have a stock of a few inverters to just replace them, and then you service the other ones while you're using your spare inverters. While you cannot have that for large central inverters. So it's easier to replace, time, cost, and reparation. And of course, one very important thing is that the OPEX, because of the energy yield, is better. So this has increased, this has shifted the trend in PV system, in which now we have higher power density converters used in photovoltaics. And here you can see 2 examples. One is from Sungrow, another is from Huawei. These are 2 Chinese companies. And here you can see both of them already reaching 1500 volt DC link, which is mainly for utility scale PV modules. And here you can see 125 kilowatt in 65 kilograms. So 2 kilowatts per kilogram. Here you can see a 1-to-1 almost ratio for this one of Huawei. So these are very lightweight. You can install this between 2 people without much need of any crane or additional stuff. Just 10 of those make a big central inverter. So this has really been a major shift in the industry, photovoltaic industry. Here you can see another example from Huawei. This one is 185 kilowatts at only 84 kilograms. Also, this is more than 2 kilowatts per kilogram with 9 individual MPPTs, 99% of efficiency. So really, really big numbers. And this is why Huawei and Sungrow, which use this technology, are currently the market leaders in new shipments, followed by other companies that were the more traditional solar inverter biggest market share. So if we use now these PV inverters, whether it's the central or the multi-string inverter I just showed you, you can use them in any of these 5 configurations. So you can connect directly a PV module or PV string to an electrolyzer, and it could produce, of course, hydrogen and oxygen, but it will be very suboptimal. So this one is not something that is done in practice. So most of the commercial systems use this approach. So you have the PV plant somewhere upstream in, and you have a large scale PV plant doing bulk generation. And the same would be the case for a wind farm. And then you go from DC to AC, from AC to the AC grid. You transmit the power to where you have your electrolyzers, and then you have a rectifier. Sometimes it's just a single stage, sometimes it's a 2-stage, and then you have your electrolyzer. So you go from this, in worst case scenarios, you can even have 2 transformers here, one to go from low voltage to medium voltage, then in the substation from medium to high voltage. Also 2 transformers over here, 2 converter stages over here, 2 power converter stages over here. So if you go even optimistic and you say 2% over here, 2% losses over here, 2% losses over here, 1% losses in all these places, you end up with quite a lot of losses before your electrons of the module gets to the electrolyzer. So at R&D level, this is not done commercially. Many people, including our group, are looking into, well, can we go directly from DC to the electrolyzer without going through AC? Of course, this would be for PV plants that are completely built for hydrogen production. This is not connected to the grid whatsoever, right? This is standalone production. And of course, you could also have a DC microgrid like it's shown over here. And at your DC microgrid, you could have also some kind of energy storage, whether it's batteries or supercaps. That could be beneficial to smoothen power fluctuations in your DC bus produced by fluctuations in the photovoltaic system. This could increase the lifespan of your fuels, from your electrolyzer. So these are variants, right? And you have without isolation, with isolation over here, and this could be with or without isolation in any of these stages as well. And of course, the DC bus could be connected through a rectifier also to the grid. So this could be a standalone DC microgrid, or it could be connected to an AC grid as well. So far, all the systems that are available are commercially are this kind of system. So you basically buy this aspect of your hydrogen, this part of your hydrogen production plant, and then you will have to negotiate with the distributor. How do you buy your power to make it renewable? So some companies can sell you specifically wind or photovoltaic energy, so you know that what you're producing is green hydrogen, right? And if we go and we are going to then look at these first ones, the commercial systems. So here you can see the PV part. We already touched this a little bit in detail before. So we have the central inverter, we have the microinverter here shown with 2 stages as it should be. And here you have the multi-string inverter and the string inverter. And here you can see then some of the topologies that I just briefly overviewed with you in that big plot there full of colors. But basically, this is the 2-level voltage source inverter. This is the T-type voltage source inverter. This is a 3-level topology. And this is the case of a NPC. If you don't recognize NPCs because the switches are just laid horizontally, not vertically, but this is an MPC structure, also 3-level, and here shown with interleaved boost converters. So these are typical, these are not the only ones that there are, but these are typical central inverters and multi-string. So this would be stuff like what you would find in the Huawei, although I don't believe it in the case of the Huawei and Kouro, it's a NPC. I believe it's just a two-level voltage source inverter. This is something you would find in a T-Make, Toshiba Mitsubishi converter, and so forth. So we already reviewed this, so I won't enter much in detail. So that's for the first part of the system. I'm going back here with the slides, I'm sorry. So that's for this part. If we look now for the second part, then the typical topologies that we use to rectify the AC current and to feed the electrolyzer are the ones that you see here. So this is a 12-pulse thyristor rectifier. This is a 6-pulse diode rectifier. That's an uncontrolled rectifier. This one is controlled, but and then here we have an uncontrolled rectifier, but followed by an interleaved buck converter. And then here we have a more traditional active front end or voltage source rectifier, which gives you full controllability of the reactive and active power over here, and also gives you better controllability for the voltages and currents injected to the electrolyzer. These are not the only ones you will find in literature. Also, not just 12-pulse rectifier, you will find also 18-pulse rectifiers, 24-pulse rectifiers. You will also find current source rectifiers. So there are quite a bit of power converter topologies that you can use over here to convert from AC to DC to feed an electrolyzer. Here you can see some of the commercial electrolyzers. So this is a market survey we made. So here you can see from 0 to 20 megawatts, MVAs, I'm sorry. And here you can see one of the, and also the ones in white are PEM and the ones in yellow are alkaline. So the largest in terms of power is 20 MVA. It's from Cummins. Then you have a fairly large Siemens PEM electrolyzer, around 17 megawatts. And here you can see also the hydrogen production rate per hour. And then just because there are so many at the lower end, we have done a zoom to this area. To here we are still in the megawatt scale. So if we make a zoom here to the kVA, then we see way more modules. And also you can see that there are quite a few PEM and quite a few alkaline. The PEM has a little bit lower flow rate, a little bit less production for the same amount of power level than the alkaline. And then continue with the market survey. Here you can see the stack nominal voltages. So this is not a single cell of the electrolyzer. So this is a stack for different brands. So you can see that most of them are concentrated around 50 volts and then between fairly low voltage, not almost everyone below 150 volts, independent of the power level, right? And then you can see they're also available with 3-phase connection in medium voltage, which is 4 to 35 kilovolts, and also low voltage 400 volts. And there are just a few, of course, in very low power for single-phase connection, which is not large-scale production, of course. If we go now to the second family of PV to hydrogen, these are the ones that do not go through AC. These go directly from DC to DC. Here we have the version in which we have transformer-less, so no isolation between the, I should say, without isolation. There are a few with transformers actually, but those transformers do not produce actually galvanic isolation. And here we have the interleaved buck, the stacked buck, the mirror buck converter, the buck boost, the couple inductor, base stop switching converter. This is a partial power converter made, and here we see isolation stage, but actually it's short circuited, so there's no real galvanic isolation. This is the so-called partial power converter based on a dual active bridge. And here we have the 3-level buck converter. So these are topologies that are suitable to be used at this DC-DC stage. Then we have the version with isolation, and the version with isolation, we have the push-pull, we have the full bridge with center tap rectifier, we have the full bridge with voltage double rectifier, we have the half bridge with full bridge rectifier, we have the NPC with current double rectifier, the two-stage interleaved. This is a two-stage. We have here one stage and here another stage, and the first stage is the interleaved buck pre-regulator, and then we have a half bridge center tap DCX converter. So this one is doing the regulation, this one is just providing isolation. And then you can combine any of these or the previous one for the topologies that had a DC bus with additional storage connected to it. So those are the topologies. And now we're coming to the end of the presentation. And I have like one question, or actually this is topic for something that you could actually chew on and take home and see how this evolved over the years. We saw during the first 10 to 15 years of PV industry heavily centered around centralization. So very big central inverters that was mainly focused on cost reduction, high efficiency of the inverter, and that was the main focus, right? And we have seen how it has transitioned to this approach over here, which is more distributed generation, taking advantage that PV power is inherently distributed. It's actually done at the cell level. And it's actually the same with hydrogen. Hydrogen is also done at the cell level, very low voltage, DC current. It's almost a 1-to-1 ratio between voltages between a PV cell and hydrogen cell, electrolyzer cell. So it really makes you wonder whether this approach from going to central power, central PV through a central inverter, through the AC network, then through a rectifier to a very, very large electrolyzer, in which everything is also done modularized. So here it's a very big electrolyzer, but inside it's also cell levels, right? But you have all your power concentrated. So it's a big funnel over here, and then you have a unfunneled over here again, right? And it makes me wonder if hydrogen is also going to go this trend in which the first 10 years it will be focused mainly on centralized generation, and then down the road cost reduction and higher energy yields and higher energy efficiencies, and actually a better levelized cost of hydrogen will go. Yes. See? Yes? Sorry. So we will reduce, this will go into this approach, and we will go directly from PV to electrolyzer at a more distributed level. Basically, this is replacing long wires by long pipes, right? So here we will have hydrogen pipes rather than electricity cables. And of course, someone will do the breakdown, the cost breakdown and the optimization to see which level of modularization will be the optimal, right? So as conclusion, green hydrogen is emerging as a viable energy carrier for energy transition applications. It's still not there yet in terms of cost efficiency, cost effectiveness, but it's emerging as one. And of course, technology and market will develop, and it's still not mature yet, but it will evolve rather fast. We have seen this happening in the solar industry, in the battery industry, in the wind industry. So there is no reason why we will not experience such a development in 10 years from now. And PV-based green hydrogen could evolve into more modular and distributed system configuration. This is what I just mentioned. This is something that we will have to see. Will it continue to go the centralized approach, or will it go the same as PV, in which the first stage is centralized and then it will go into more modular configurations. So at the end, there's plenty of room for research, development, and innovation. So if you work in this area, kudos to you, because there will be a lot of work for the next 20 years. So that's my presentation. And with that, I'm open to some questions.
Thank you, Samir, for your presentation. We have some questions in the chat. I will read.
Okay, so there's one, as far as I understand, this one is from Gabriel Cisternas. This one says, as far as I understand, hydrogen causes brittleness on regular pipes currently used with natural gas, leading to cracks. I wonder if we have a sense of environmental and economic impact related to replacing, upgrading the current distribution infrastructure. That's a really good comment. I haven't gone in depth on that area. It's not my field of research, but you know, I remember when I was talking with some guy about wave energy, right? Completely off topic, but you will get the point here. And I was telling, and of course, I'm not someone expert in corrosion of materials and stuff like that, exposed to salt water and so forth. So I said to them that I was a little bit skeptic about how wave energy would evolve, because you know the corrosion in the sea and whatever. And he told me, you know, yeah, it's true, it's new technology for the energy sector, but you know the people making ships and you know and oil rigs, we have been doing ships for decades, and there's quite a lot of know-how on that end. So the same happens here. Hydrogen is not something new, and it's not that it's the first time that we so there are technologies available, cost effective for this. So the only thing here is what you actually point out in your question, if we will be able to use existing infrastructure, or we have to invest in completely new one. And unfortunately, I'm not an expert in that area, so I won't be able to give you a good answer to that. But what I see here is that the oil and gas industry is keen on having a big piece of this cake, right? So they will convert their systems in such a way that they can transition from fossil fuels to green hydrogen. Otherwise, it will end up out of business. And also the green energy sector also wants to increase their capability of production of green energy. What I mean by that, they want to increase demand. For example, in a place like Chile, where we have just a 25 gigawatt system, it is very interesting for these energy companies to produce more, to have higher demand. If they have higher demand, they can install more PV parks and more PV plant and wind farms. So they will invest in the infrastructure in order to get this market. It's the same when we had the first cell phones, and you would say, okay, but we cannot use the radio and TV antennas. We will have to have new cell phone antennas. But there was a big industry that wanted that market, and they invested in that. So at the end of the day, I'm not that worried about that, because there are so many people hungry of the hydrogen market. So it will come. Next question. Remember that you write your, okay, that's not a question. So someone is asking here if the presentation will be shared to the public. I believe it is. I believe, Nicolas, that this is being taped and then will be uploaded to YouTube, right? Yes. So it will be
in the description of the YouTube video.
Exactly. And another question from M. Carrasco. Unfortunately, I don't have your first name there, but M. Carrasco says, can I replace my conventional diesel generator, 150 kVA, for some hydrogen alternative? These chants are in Chile. I have an off-grid concrete production plant. I'm not sure if I'm getting the question right. So you want to, okay, now I'm getting the question. So you want to have a, that's not the case of an electrolyzer. Then we are talking about a fuel cell. So what I understand from you is you want to produce electricity, and instead of using your diesel generator, you want to have hydrogen and then have a fuel cell to produce electricity. Is it that? If that's the case, yes, you can buy fuel cells, and yes, you can buy a tank to store hydrogen, and yes, you can buy hydrogen. It won't be that cost effective. It will be more expensive though. Yeah, that's my answer to that. Then I have Nicolas Gonzalez is asking, hi Anton, yes, it will be available in the description on the, okay, that's the answer to the previous question. Then Gabriel Sistemas, okay, that's also not a question. And then Ian Illanes, oh, I know this guy. long time no see, Ian. I hope we studied together, so it's from same generation. Yeah, it's that Ian. In your opinion, what could be done from the power electronics perspective in order to contribute to a price drop down to generation? Okay, that's a very good question. So what I think, I have actually had this discussion with people from the power converter industry and the electrolyzer industry, and I've always gotten to this point. So the biggest cost currently for the hydrogen, for the levelized cost of hydrogen, is in part the OPEX, which comes from the cost of the energy, and the CAPEX, which comes from the electrolyzer itself. The power converter is not the most expensive part of the system, but the power converter, if you choose it wisely, like what I'm saying here, if you make a different decision, it could lead to an architecture that down the road, once the technology is mature and the systems are optimized, you reach a lower levelized cost of energy. So I don't think that we are at this point right now, because now you can retrofit existing technology, you can buy all these things and you can put them in place, and because you can buy them, of course, they are cheaper than something that you have to develop. You cannot go and buy these things off shelf. I mean, you can. This one is from Enapter. So Enapter is selling these smaller electrolyzers. These are alkaline membrane electrolyzers. And you could put some of them in a container as they suggest, and you could match that power level to one of these. But then, of course, you will end up with having non-standard pipes and also tanks and everything. So still, the whole value chain of technology is not optimized to actually lead to a distributed configuration that is more optimal than the one that you see above and more cost effective. But down the road, it could be. And of course, you can improve topologies that are more efficient in any of these configurations and then have lower losses. Perhaps maybe one of the biggest things that you can contribute to reduce the levelized cost of hydrogen is something that is also being looked at to reduce the levelized cost of photovoltaics, which is to make them more reliable. So from a power electronics perspective, the power converters are not the most reliable piece in this in the whole system. Actually, the PV modules are the most reliable. They go for 25 years, even 35 years. The transformers are the electric transformers are way more reliable machine in all the system. Also the transmission lines, and then the fuel cells. I mean, the electrolyzer is also not very reliable. But since you asked for the power electronics, I think, yeah, improving efficiency, modularization, and improving reliability are things that definitely could impact the cost of hydrogen. Very good questions, by the way. We have another question here from Francisco Moraga. He says, would the direct connection between the PV plant and the electrolyzer be more cost effective than an indirect connection through the grid, considering that the transmission has an additional cost? Well, that's one of the things that I think it is. If your primarily goal of your PV plant is to just produce hydrogen, you will only use it to produce hydrogen. Why convert it to AC and transmit it over a large distance and have your electrolyzers, let's say, 1 kilometer away. Remember that this over here can be several kilometers in length, right? And while you can have electrolyzers put on besides every group in a modular way, right? So then it comes really to what's more expensive: electric cables or piping, and you could even have optimize. The only problem here, and this is something that nobody has asked yet, is what happens during the night. So the problem is that with you don't have your system available the whole time, and that's also impacting the levelized cost of hydrogen. That also happens with wind energy. So wind energy does work during the night, but it's also fluctuating during the day. So you might not have winds during daytime. So, but if you see a power plant factor, of course, the power plant factor is higher on a wind farm. If it's well located. So you will use your electrolyzer more, and that will impact the levelized cost of hydrogen. So a thing that you could do is one thing that we can hope for is that, of course, cost will go down. So the time usage becomes less and less relevant. And the other thing is that you can oversize your PV plant also because the size goes down. So if PV power goes to $10 the megawatt hour instead of 20, which you could find in another energy source, then you could install twice the PV systems, and then you can have better use of your electrolyzers, for example. Or you can also install some kind of energy storage. It can be done with CSP. So it could be also a good option to mix photovoltaic with CSP, which is concentrated solar power. You can store energy and work during the night, having almost 100% availability of your system if you size it properly. So at the end of the day, yeah, those are the factors that could really impact the levelized cost of energy.
So thank you, Samir, and thank you to all the audience for the questions. So we are on time to finish this session. So if you want to say some words to the audience to conclude. Yeah,
well, I would really thank you, the organizers, for providing me this platform to give this talk. I really think that, I mean, it's not just a figure of thinking. I mean, it's green hydrogen is going to become a key player in the energy sector and in energy transition technologies and in the offset of carbon footprint and so forth. So, and this is a good time to be working on these topics because there is a lot to do in maturing some technologies over here. We are at the beginning stage of the S-curve, if you know the S-curve of innovation. So we are basically where photovoltaics was in 2005. We are at the same point here for green hydrogen. There are quite a lot of things and challenges to overcome. Of course, if you talk to someone which is selling you a bundle of electrolyzer and everything, they will tell you it's a very mature and proven technology. But if you talk with the actual people operating those systems in practice, they will tell you that there are quite a lot of challenges. And then if you take it a step further, there are also challenges in if you want to build the infrastructure for distribution and transportation to get to these new applications, not to the applications that we have currently available, but rather the new ones like electromobility and so forth. And there are even more challenges if you want to really go into the liquid synthetic fuels, which is, to me, one of the most interesting parts of hydrogen, since it will enable us to fly planes and ships as we have right now, which is the area of technology where electrification is really lagging behind. So yeah, it's a good time to be a chemical and electrical engineer at this time.
Thank you, Samir, for your words, for your last words. And thank you to everyone who was here with us today. And remember that in 2 more weeks, we will have another session of W-ENER. So we will see you soon. Goodbye, Samir. Goodbye to everyone.
Bye-bye.
Thank you, everyone. Have a good day.
Thank you.
Thank you.
Bye.
Bye-bye,
Thanks for
everyone.
the presentation.
Bye.
It's really interesting.
Very nice presentation, Samir. Good to see you again. Bye-bye.